Okay, so I have started the live. Just check and confirm. So am I audible to you? Everything is clear? Yes, what?
We are able to hear your voice clearly.
Okay. So I have started the streaming on YouTube. You just can click on the link. So I have sent to you. You can use the Discord for voice communication if you have anything to ask or anything. Or you can also use the live chat section in the YouTube. So everything is okay. So everyone just reply me on live chat. You have an access for the live chat also. So everyone from Discord, click on the link which is basically the YouTube link. So click on the link to join the live classes. Okay. So everyone on Discord, just click on the link. So if everything is everything okay? Just reply me on live chat. Those who have not replied.
Yes, sir. Everything is okay.
Okay, okay, fine. Okay, so we'll start the topic statistical inference, and so we'll start a basic of, let's say, statistical inference today, and the next day we'll do the advanced parts and examples and everything. So statistical inference can be divided into, let's say, two parts, which is estimation and the another one is basically testing of hypothesis. Okay, so we'll start with this topic, which is basically the estimation, and estimation can be divided into two parts, which is point estimation and the another part, which is basically interval estimation. Now I'm confirming that you need not to worry about these class notes or everything. So I'll send the class note in details, and obviously I'll send the recorded video on your registered mail ID. So we'll start with this point estimation first and interval estimation later. So let's say point estimation. So what is point estimation? The question is, right, what is point estimation? Now, why should we call this as point estimation? So let's say the problem of point estimation. So the problem of point estimation is to pick or select, okay, so is to pick or select a statistic which is, let's say, capital T. Okay. Now, these statistics, so we all know that statistics basically a function of the sample values. Okay. So we can call that capital T by capital T of x curl. Okay. So x curl means, so x curl basically a vector which is x1, x2, xn. Okay. So that means the sample values. Okay. So capital T basically the function of all the samples. So that's why it's a statistic. So a statistic can be denoted in this way. Okay. That based estimates the parameter theta. Okay. Now what is parameter? So parameter is basically the unknown characteristic of the population. Okay. So parameter basically the unknown characteristic of the population, and so theta is basically unknown to us, and parameter is always fixed. Parameter is not variable. Random samples are always independent. Yes, Anurag, random samples are always independent. Okay. So if, let's say, if in question you were given that it is a random sample, so it always be independent. So the parameter is theta, and theta is unknown to us as parameter is always unknown, and theta is also fixed. Parameter is always fixed. So parameter cannot be a variable. Okay. In some sense. So capital T can be written in this form, and capital T is called the estimator of theta. Okay. And capital T is basically a function of these x1, x2, xn, or function of this random sample. So that's why it will give a particular value, and that's why we can, let's say, we can say it is a point. Okay. Using which we can estimate the value of theta. Now such statistic capital T, so such a statistic capital T is called an estimator of theta. Okay. So capital T is basically an estimator of theta, and the value of capital T, which is basically T x curl, we can say that, or for any observed value of this capital X curl. Now, what is observed value of capital X curl? So let's say if we have a random sample which is capital X1, X2, Xn, then the observed value of capital X curl is like, observed value of capital X curl is small x1, x2, xn. Okay. So for some, let's say for n individuals or for some k individuals. Okay. So this is the observed value, and this is the actual value. Actual value means this is the random variable, and this is its observed value. So if we have a particular observed value, let's say small x curl, so this is denoted by small x curl, then the observed value of capital T. So observed value of capital T can be denoted by, let's say, capital T of small x curl is called the estimate of theta. So this is called the estimate of theta. That means capital T is basically estimator of theta. Okay. And the observed value of capital T is called the estimate of theta. So estimate and estimator obviously different. So estimate is the value of the estimator, or you can say like observed value of the estimator. Okay. Now, what is observed value? So observed value is basically based on, or observed value is that value which is based on the given sample. So if you have, let's say, if you have the random variables x1, x2, xn, and it is given to us that x1 takes the value 1, x2 which takes the value, let's say, 4, and xn takes the value, let's say 10. Okay, so then based on these particular values, we can construct these capital Tx curl, and which will be the estimate of theta. Yes, Akash. So I have explained this part, which is observed value. So let's say if we have random sample x1, x2, capital X1, x2, xn, and then if we have given the particular sample values of capital X1, x2, xn, then based on that sample values, or you can say that these sample values are basically the observed values of capital X1, x2, xn. Okay. Or for example, so let's start with a small example. So let's say if we have two random variables, let's say x and y, and these random variables x denote the height. Okay. So let's have an example for that. So let's say here is a school, okay, and so there are, let's say, class 1, class 2, and up to, so let's talk about class 1, class 2, and class 3. Okay, and we want to, let's say, we want to survey about the height of each and every class. Okay, so let's, the variable, the main variable is basically height. So we have taken a random sample, let's say capital X1, X2, Xn. Okay, so which is basically the height of n individuals, but these are random samples. So random samples means these are random, these can take any values. Okay, so now if we choose n members from class 1, if we choose n members from class 2, and if we choose n members from class 3, then let's say in class 1 we have 50 members and we have chosen n members. So let's this n be 10. Okay, so let's make this n be 10. Now each and every class, let's say, have 50 members or 50 students, and we have chosen 10 students randomly from each and every class. Okay, now this is basically my random sample. Okay, this can take any value. Now for class 1, these values, so for class 1 these values of x1, x2, x10 is obviously different from the values of class 2. Okay, or from the chosen values from the, let's say, from the chosen students. So for class 1, let's say the values are, so from class 1, the values are, let's say in centimeter, okay, so 123, 133, and 142. Okay, so these are basically heights in centimeters. Okay, so this is for class 1, but let's say for class 2 we can have different 10 values like 131, 116, and 136, and so on. Okay, so for class 3 also, so that means this x1, x2, xn is basically the heights of 10 individuals, and this is a random sample. And why it is random? As it can take randomly different values for different classes. Okay, Akash? So now the next part, which is what is interval estimation. Okay, now the estimation procedure works like, let's say if we have a population. Okay, so if we have a population and the unknown characteristic of the population is basically theta. So let's say we don't know about the average height of the population, then that average height will be the parameter of that population. Okay, so let's denote that by theta. Now To get that value of theta or to estimate that value of theta, we just take a sample. So we just take a sample from that population. Okay, and based on that sample, we can estimate this value of theta. And let's say capital T. So capital T is basically a statistic which is a function of the sample values. Now using this capital T, we can estimate the value of theta. Now obviously the question arises like capital T is based or not, or capital T is better or not. So that's another question. So I will discuss that part later. Okay. But we can estimate the value of theta using this capital T or using any capital T. So we can have infinite number of capital T. Okay. Now this procedure is called the estimation procedure. Now under which we have point estimation. That means we have exactly a value of t, which is, let's say, small t skull, and which can be written as the estimator of theta. So theta is unknown to us. Theta hat basically the estimated value of theta. So t skull can be thought of the estimated value of theta. Okay. Similarly, for interval estimation, so for point estimation, we can give, let's say, a particular point which is basically the estimator of theta, or you can say which is the estimate of theta. Okay. But for interval estimation, the problem of interval estimation, okay. So the problem of interval estimation is to define, let's say, a pair of statistics, let's say capital T1 and capital T2. Okay, so we have defined a pair of statistics which is capital T1 and T2 such that this interval, which is basically T1 and T2, so this interval contain the value theta, okay, or contain the parameter theta with certain probability which is gamma. Okay, and this can be evaluated. Now, what does that mean and how it differs from the point estimation? So for point estimation, for point estimation, we can get the value, let's say capital T of small x skull, and which can be thought of as the estimator or the estimate of theta. Okay. Now, in interval estimation, we cannot, let's say, get a point or cannot get a particular point which can be used as an estimator of theta. Okay. So that's why we can use this interval. Let's say this is basically an interval T1 and T2, and we can assure that this interval T1 and T2 will contain the value theta. Okay. So this means will contain the value theta with some certain probability. Okay. Now, if this T1 and T2 or this interval is, let's say, smaller, then obviously that interval would be better for us. Let's say the actual value of theta is like 5. Okay. So someone tell me that minus 100, 200. So this interval contains the value of theta. So obviously that is right. Okay. But someone tell me that minus 10 to 10. So this interval contains the value of theta. So obviously this is more correct than this, as the interval is basically shorter, or let's say the interval is basically smaller than this interval. So the interval estimation, the concept of interval estimation is to get a smallest interval or a shortest interval. Okay. Now we will discuss this interval estimation procedure later. So first of all, we will discuss the point estimation. So you need not to worry about writing these class notes. So I'll send the recorded video. You can write that later, obviously. So try to understand all the topics. So now the next part, the requirement of a good estimator. Okay. So obviously under the point estimation. So obviously this is under point estimation. So the requirement of a good estimator. So how can we say that an estimator is good or not? So let's say, so let capital T be an estimator of theta. So how can we say that capital T is good or not? As capital T is basically function of capital X skull. Capital X skull is a random sample. Now capital T basically a function of capital X skull. So as we know, capital T is function of capital X skull. Now capital X skull basically the random sample, and capital T is the function of that random sample. So that's why capital T is also random. Okay, so a function of random sample is always random. Okay, now the measure of closeness. Okay, so the measure of closeness, let's say mod of t minus theta. Now what does this means? So mod of t minus theta measures the closeness between t and theta, or you can say like the distance between t and theta. Now the distance can be positive or negative, so that's why we have given this modulus portion. Okay, now measure of closeness, which is mod of t minus theta, is also a random quantity. And why it is random? As capital T is random, so that's why mod of t minus theta, which is a function of capital T, is also random. Okay, now in our context, we can have two measures, two basic measures of closeness. Okay, now these two basic measures of closeness are so number one, which is probability of mod of t minus theta. Okay, that means the distance between t and theta is less than epsilon. Okay, so where epsilon is very small. Okay, so for, let's say, mod of t minus theta is less than epsilon, and we have to calculate the probability of that for any epsilon which is greater than 0. Okay, so this is the first measure of closeness, and the second measure of closeness, which is number 2. Now the second measure of closeness is expectation of mod of t minus theta whole to the power r. Okay, and for some r which is greater than 0. Okay, so this is basically the two measure of, or these are basically the two measures of closeness. Now why it is called the measure of closeness? So if capital T is a good estimator for estimating the value of theta, then the distance between capital T and theta must be smaller. Okay, that means this distance, which is modulus of t minus theta, so this distance will be smaller, or this distance will be the lowest. Okay, So that's why if this distance is less than some epsilon, less than some epsilon means less than any positive epsilon. So this positive epsilon can be, let's say, any small quantity which is close to 0. So this modulus or this distance is less than epsilon, and this probability, if this probability close to 1, then we can say that capital T is basically a good estimator of theta. Okay, that means the probability of the distance between T and theta is very small, and that probability is much more higher. That means capital T and theta will be much more close to each other. So this indicates, so that's why capital T will be a good estimator for theta. So now, if capital T is a good estimator of theta, then this first one, then number 1, probability of mod of T minus theta less than epsilon will be close to 1 for all, or let's say for epsilon greater than 0. Okay, that means the distance between T and theta will be small, and that probability or probability of occurring that event is basically larger. Okay, and the second one, now what does this mean? Second one means if T and theta are close to each other, that means they can have the distance like fractional quantity. Okay, so then that to the power r will also be smaller. So if modulus of T minus theta is small, then modulus of T minus theta to the power r is also small. Okay, then expectation of that quantity is also small. Okay, so T and theta, if T and theta are close to each other, then this quantity will be small, and if T and theta are close to each other, then T will be a good estimator for theta. So that's why if this quantity is close to 0, or if this quantity is small, then we can say that capital T is a good estimator of theta. So that is number 2, which is expectation of mod of T minus theta whole to the power r is small. Okay, so if this is small, or you can say that is close to 0. Okay, so if this quantity is close to 0, then capital T will be a good estimator for theta. Any question from this part? Okay, so then let's go to the next part. Now, based on this closeness and everything, we can have 4 properties. So there are 4 properties of estimators. The first property is minimum mean square error. Okay, so this mean square error can be written in a short form like MSE. Okay, so minimum MSE. And the second one, or the second property, is consistency. Now the third property, sufficiency. The fourth property is basically completeness. Now, so we will start from this first one, which is minimum MSE, or you can say like minimum mean square error. So let's start with the first one, which is minimum MSE. Okay. Now in statistics, so this type of short form, which is MSE, now this type of let's say short notation or short form can be simplified in this way, like in doing the backtrack. Okay. So first of all, we just have to get the error. So what is error? Error means, so we want to estimate theta using the value of capital T. So then the error will be the distance between T and theta. As we want to estimate the value of theta using the value of capital T, so the error will be like capital T minus theta and modulus of capital T minus theta. So this is my error. And then for A's, it is square. So then the square, and capital T is a random variable. So that's why for, let's say, for mean or for the last mean part, we just have to take the expectation. So Akash, so in second part, T minus theta must be in fraction. It is necessary. No. So this is not necessary part. So I have told that if T minus theta is very small, then it will be a good estimator. Now it doesn't mean that T minus theta is always very small. Okay, Akash. So this is first error, then square, and then mean. So that's why we get this quantity, and this is called the MSE or mean square error. So let capital T be an estimator for estimating theta or estimating the parameter theta. So estimating the parameter theta, then that MSE can be defined as like, so MSE of what? MSE of capital T. That means mean square error of capital T in estimating the parameter theta. So that's why we can write in this way, and that is exactly expectation of mod of T minus theta square. So you can just remove the modulus part. So you can write in this way. Okay. So this is my MSE. Now how can we get a best estimator using this MSE? Or how can we get a good estimator using this MSE? So I'm telling you that in this lecture series, I will not prove any detailed, let's say, theorems or anything, as this is specially lecture series for the competitive exam. So that's why I will discuss the results and the concepts and all the shortcut techniques only. Okay. So now this MSE, so MSE is basically one type of error. Now we all know that a estimator is good if it has minimum error. So that's why if we have a minimum MSE, that estimator will be better. Okay, so that's why the tagline, you can say like this is our tagline, which is smaller the MSE, better the estimator. Okay, so if the MSE is small, then we can get a better estimator. So that's the process. Now let capital T naught be another estimator of theta. Okay, so capital T be an estimator of theta and capital T is another estimator of theta. Then capital T will be better than capital T naught. So as capital T and capital T naught both are estimating the value theta, so capital T will be better estimator than capital T naught if MAC in estimating theta, the value of capital T is less than the value of T naught. Okay, and this is true for all theta belongs to omega. Now what is omega? So you can say like omega is the parameter space. Now what is parameter space? So parameter space means if we have, let's say, normal mu comma 1 distribution, we define mu belongs to real number. Okay, so this real number is basically our omega. So this real number can be thought of as the parameter space. That means in which space or in which space parameter, all the parameter values are stored. Okay, so let's say if we have mu sigma square, then sigma square is always belongs to r plus. So r plus means positive real number, or you can say like greater than 0. So then r plus will be the parameter space for sigma square. So that's called the parameter space. So this omega is basically the parameter space. So capital T will be better if its MAC is smaller than capital T naught. Now here comes the concept of unbiasedness. So how can we get the concept of unbiasedness? So a note which is MAC of capital T can be written in this way, which is T minus theta whole square. Okay. Now simplifying this part, we can get T minus expectation of T plus expectation of T minus theta whole square. Okay. Now we all know that capital T is a random variable. Then expectation of capital T is basically a constant quantity, as expectation of any random variable is constant. Okay. So we can write this as expectation of T minus expectation of T square plus expectation of minus theta square plus 2 into expectation of T minus theta into expectation of T minus expectation of T. Okay. So this quantity, just A plus B whole square form. Now simplifying this part, we can get, so this is basically my variance of capital T. I think you all know the formula of variance, which is expectation of random variable minus its expectation and then square. So that's why this can be written as variance of capital T plus, so this quantity, now expectation of T is constant and minus theta, I have told you that theta is always constant as it is a parameter. So that's why this whole quantity is constant. Now constant, so expectation of any constant quantity is constant. So that's why you can write this as expectation of T minus theta whole square. Okay. Now in this part, expectation of T minus expectation of T, what will be the value of that? Expectation of T minus expectation of T is basically expectation of T minus expectation of T, and which is 0. If you don't know this concept, you just have to read the basic formula for the expectations. Okay. Now this is 0, so this whole quantity or the product term is basically 0. So that's why MAC of T can be written in this form, which is variance of T plus this quantity. Now this quantity is called the bias of capital T. Okay, so that's why we can tell like this is bias of capital T. Okay, and the square. Okay, so What is bias? So expectation of t minus theta is called the bias of capital T, or you can say, or you can define like b t theta. Okay, so simple. Now here comes the concept of unbiasedness. So if bias of capital T, like expectation of t minus theta, is basically 0, then we can call that capital T an unbiased estimator of theta. Okay. So here comes the concept of unbiasedness. So if bias t theta, which is basically expectation of t minus theta, equal to 0. Okay, so if this bias is equal to 0, then we call capital T an unbiased estimator of theta. Okay, so we call capital T an unbiased estimator of theta. That means capital T is unbiased estimator of theta if expectation of t is equal to theta. Okay, so we can write the formal definition. So if expectation of t is equal to theta for all theta belongs to omega, then capital T is unbiased estimator. Okay, so this UE means unbiased estimator of theta. Okay, now this is the concept of unbiasedness. Now we have written a tagline which is smaller the MSE, better the estimator. Now if MSE is small, that estimator will be better than other estimators. Okay, now MSE can be written in this form like variance of t plus bias of t square. Okay, so we all know that variance of t is always greater than equal to 0. Okay, and bias, we can say like bias of this and square. So obviously a squared quantity is always greater than equal to 0. So these two quantities are non-negative. So hence the smaller or the smallest value of these two quantities is exactly 0. Okay, so MSE will be small when MSE is equal to 0. So that's why variance of t will be equal to 0 and bias of t theta square will be equal to 0. But these two cannot occur together in practical sense. So now to get a smaller MSE, we have to minimize the variance of t. Okay, so to minimize this MSE or mean square error, we have to minimize this variance plus we have to minimize this bias square part. So we have to minimize the variance of t and expectation of t minus theta square part. Okay, now here comes the concept of uniformly minimum variance. Okay, so not uniformly. So here comes the concept of only minimum variance, not uniformly now. So here comes the concept of minimum variance unbiased estimator. Okay, so UE means unbiased estimator. Now in short we can write this as MVUE. So how? As we have to minimize the MSE, and MSE is basically variance of t plus this bias of t square. So if we get, let's say, the minimum value, or if we minimize the variance of t and bias of t both, so then we can get an estimator which is called the minimum variance unbiased estimator. So why it is minimum variance? As we have minimized the variance part. And why it is unbiased? As we have minimized this biased part also. So biased part will be minimized if this is equal to 0. Now if this is equal to 0, then we can call capital T as unbiased estimator. So that's why minimum variance unbiased estimator. Okay. So but here is a note for that. So you can call it as a disclaimer also, that in practical sense, so in practical sense, if variance of t decreases, then bias of t increases. Okay, and it is in practical sense, and vice versa. Okay, and vice versa. Now what does that mean? That means if, let's say, variance of t decreases, then bias of t increases, and if bias of t decreases, then variance of t increases. But this is for practical sense. Okay, but in theoretical sense, we can just think of like, but if we just let's say minimize the variance of t, if we just minimize the bias of t, we can get a minimum MSE. So that's the theoretical concept, but in practical concept we get this quantity. So then we get a concept of bias variance trade-off. Okay, then we get a concept of bias variance trade-off, but this is not in our lecture series, or this is not the part of our lecture series, so that's why I'm not discussing this part. But in practical sense, if we work with data, then if you want to minimize the variance, then the bias will increase, and if you want to minimize the bias, the variance will increase. So that's why we have to do a trade-off. So trade-off means a balance in between the bias and variance, so that we can get a minimum MSE. Okay, and this method is also applicable for the big data parts, or you can say like machine learning parts. Okay. Okay, so let's go to the next concept. So results. So the first result is the sample raw moments are unbiased estimators. Okay, so the sample raw moments are unbiased estimators of population raw moments. Okay, I think you all know the concept of raw moment. So variance of t cannot be exactly equal to 0. The concept is like variance of t is, if the variance of t is equal to 0, that means if variance of t is equal to 0, so the question is from Indrashish. So the variance of t, if the variance of t is equal to 0, then expectation of t square will be equal to 0. Okay, and then we get t will be expectation of t with probability 1. So That's a result. Okay. So if variance of t is equal to 0, then we get capital T will take only the value expectation of t. Capital T will not take any other values. So this WP means with probability. So capital T will take only the value expectation of t with probability 1 if variance of t equal to 0. Okay. But most of the time variance of t cannot be exactly equal to 0. Now, so let's continue this result. I'm removing this part. Okay. So the sample raw moments are unbiased estimator of the population raw moments. And what does that mean? So that means sample raw moments are basically MR dash. Okay. Now in usual sense, we can define this mathematically like 1 by n summation of xi to the power r. Okay. So 1 by n summation of xi to the power r is called the sample raw moments. If we have, let's say, the sample capital X1, X2, Xn. Okay. So if we have random sample capital X1, X2, Xn. Okay. Now what will be the population moments or population raw moments? So the population raw moments denoted by mu r dash. Okay. And which is the rth order raw moment of the population. Okay. So that is denoted by mu r dash. I think you all know that. Now the result says that, so using result, expectation of mr dash is basically mu r dash, or you can say like expectation of 1 by n summation of xi to the power r will be exactly mu r dash. Now what does that mean? So if we take different values of r, so if we take, let's say, r equal to, so for r equal to 1 to k. Okay. So that is expectation of 1 by n. So if we choose r equal to 1, then expectation of 1 by n xi to the power 1, which is basically xi, so it will give the value mu1 dash. Okay. So 1 by n summation of xi is nothing but the mean of the capital x1, x2, xn. So this is capital X bar. You can say like expectation of X bar, and which is mu1 dash. Okay. Similarly, if we choose, let's say, 1 by n summation of xi square, and for example, if we choose 1 by n summation of xi square, I running from 1 to n, you will get the value mu2 dash. So this is basically mu2 dash. Okay. And similarly, for different values of r, you can get different unbiased estimators. And that's a simple result. Now let's go to the next result. So let's go to the next result. So next result is basically the sample variance, which is, let's say, small a square, and can be defined as 1 by n minus 1 summation of x bar square. So let's define this by capital A square. So this is called the sample variance. Okay, so the sample variance is unbiased estimator of population variance. Now what does that mean? That is expectation of A square is basically exactly equal to sigma square, where sigma square is the population variance. Okay. Now the next result if we have two unbiased estimators of, so if we have two unbiased estimators and two different unbiased estimators, okay, so if we have two different unbiased estimators of a parameter theta, then we can have infinitely many estimators. Okay, so we can have infinitely many estimators. Now how can we prove that? So I'm not proving the whole part. So let's say if we have two different estimators, let's say capital T1 and capital T2 of theta. So proof hint, if capital T1 and T2 unbiased estimator of theta, then expectation of T1 will be equal to theta and expectation of T2 will also be equal to theta, as T1 and T2 are unbiased estimator of theta. So this property holds. Now let's take a convex combination of these T1 and T2. Okay, or you can say like linear combination, not convex combination, a linear combination of T1 and T2. So let L1 T1 plus L2 T2 be another unbiased estimator with L1 plus L2 equal to 1. Okay, and why it is an unbiased estimator? If we take the expectation of L1 T1 plus L2 T2, so if we take the expectation of L1 T1 and L2 T2, then it will give L1 expectation of T1 plus L2 expectation of T2, and which is L1 expectation of T1 is basically theta plus L2 into expectation of T2, which is also theta, which is theta into L1 plus L2, and exactly theta, as L1 plus L2 is basically 1. Now this L1 plus L2 is basically 1 and L1 L2 belongs to real number. We can choose infinitely many L1 and L2 such that L1 plus L2 equal to 1. For example, so let L1 equal to 0.1, L2 equal to 0.9. So L1 equal to 0.2, L2 equal to 0.8, and so on. We can choose infinitely many L1 and L2 such that L1 plus L2 equal to 1. So that's why we can get infinitely many unbiased estimator of theta, but provided there are two unbiased estimator of theta. So if we have two different unbiased estimator of theta, so then we can have infinitely many unbiased estimator of theta. So that's the property. Any question from this part? Okay, so now let's define some basic concept. The first concept is on indicator function. So we have to use this concept a lot. So what is indicator function? So let's try with a basic definition first. So a definition. So a indicator function of, let's say, of a subset capital A of a set, let's say capital X, is a function such that so is a function which is denoted by 1a. So we can use many other notation also, let's say I of a or any other notations. So I will discuss that notation later, but so let's define this by 1a, which is a function from capital X to 0 1. Okay, now within second bracket if we write 0 1, that means the values 0 and 1 individually. Okay, where 1a of, let's say, X is defined as, okay, so this notation means 1ax is defined as 1 if X belongs to A and 0 if X doesn't belongs to A. Okay, that means if we have, let's say, capital X, which is the domain, and if we have a subset which is capital A, okay, so if we have a subset capital A in X and there is a function called 1a, and this is my domain, but the domain members are basically 0 and 1. Okay, so if we choose any member from this capital A, so that will map to, or that will be mapped to 1, and if we choose any member, let's say other than capital A, that means from these parts, so let's say from these parts, okay, so then after 1 or after applying this 1a, we can get the value 0. Okay, so this is the idea of indicator function. So indicator function always takes two values, which is 1 and 0. Now it is also defined as I suffix a. So 1 suffix a, or you can similarly denote it by I suffix a, or let's say chi suffix a, or you can denote it by kappa. So this is basically the notation kappa. So kappa suffix a. But in most of the time, we will denote this by IA or 1a. Okay. So now let's define, or let's describe some basic properties of this indicator function. So which will be useful in our context. So properties. So number 1. So the first property, if A and B are two subsets of capital X. So let's say if we have capital A and capital B, basically two subsets of capital X. So if this happens, then I of A intersection B. So in our example, we don't have an intersection part. But if, let's say, capital B like this, then A and B must have some intersection part. Okay, so if IA intersection B, so IA intersection B can be defined as minimum of IA and IB. Okay, so I'm not proving any part. So IA intersection B can be defined as minimum of IA and IB, and which is basically IA into IB. Okay, so IA into IB. So IA and IB. So that means I of A intersection B will be 1, or will take the value 1 if IA equal to 1 and IB equal to 1. Now if IA equal to 1, so then X belongs to A. Okay. And if IB equal to 1, then X belongs to B also. Okay, so IA and IB will be equal to 1 and 1 if X belongs to A and B both. That means X belongs to A intersection B. So that's why we can write I of A intersection B, or indicator function of A intersection B, is basically IA into IB. Okay, and I of A union B. Okay. So I of A union B will be max of IA and IB. Okay. So max of IA and IB, and which can be written as IA plus IB minus IA into IB. Okay. So in this way, so you can say like A union B means A and B both. Okay, so that's why you can write in this way. So A union B means A or B. So this is the basic property of the indicator function, and the second property, so the second property, the number 2, I of A complement can be defined as 1 minus I of A. And why? So I of A complement means it will take the value 1 and 0. So it will take the value 1 if X belongs to A complement, and if X doesn't belongs to A complement. Okay. So now this can be written as like it will take the value 0 if, so X doesn't belongs to A complement, that means X belongs to A. Okay, so that means X belongs to A, and 1 if X doesn't belongs to A. So these both are basically similar. Okay, now if we define IA of X, so that would be 1 and 0 if X belongs to A, and if X doesn't belongs to A. Okay, now if we take 1 minus IA of X, so then 1 minus IA of X will be 1 minus 1, that is 0 if X belongs to A, that means this value, and 1 minus 0 will be 1 when X doesn't belong to A, that means this value. So that's why 1 minus IA of X is exactly equal to IA complement X. Now the third property, so let's say expectation of IA. Okay, so if let's say capital X is a random variable, then expectation of IA can be defined as, or you can say like this, so expectation of IA, so it will be like integration. So we all know that expectation means integration. So integration over the range of capital X. So this range can be defined as capital X, then IA of X and dp. Okay, so this is basically expectation of any quantity is that value into its corresponding PDF. Okay, or you can say this is like d of f. Okay, now d of f, where capital F is the CDF, we all know that if we let's say differentiate capital F with respect to some x, so then it will give the PDF value. Okay, as we know that expectation of x is basically for continuous random variable, it is x into fx dx. Now this fx dx can be written in this way, d of fx. Okay, and why? As we know that d dx of fx is basically small fx. So where capital Fx is the CDF and small fx is the PDF. So if we, let's say, differentiate capital Fx with respect to x, we'll get the PDF. So that's why d of fx can be written as fx dx. So simple. So that's why we can write this fx dx by d of fx. So similarly in this way. Okay. So expectation of this quantity is basically value into its corresponding PDF. We can write in this way, but IA, so IA takes the values 1 and 0 only. So that's why if IA equal to 1, the integration is valid. If IA equal to 0, integration is invalid. Okay. But IA, you can say like IA is 1 if X belongs to the region capital A or X belongs to the set capital A. So that's why this integration is valid only on the set capital A and then d of f, you can say like this. Okay. Now d of f can be thought of like fx dx, so you can thought like that. Okay. Now if we do integration of fx dx over some region capital A, so that will give the probability of capital A. So that's why expectation of any indicator variable is basically the probability. Okay. That means if we have defined an indicator variable like 1 and 0, if x belongs to A and if x doesn't belongs to A, okay, then the expectation of IAX will be probability of A. So for example, if we choose A equal to, let's say 0 1, this set, okay, so if A equal to 0 1, then expectation of IA of x will be probability of x belongs to 0 1. So probability of A means probability of x belongs to, so we can think of like probability of x belongs to A. Okay, so that means probability of x belongs to 0 1. So for example, any question from this part? And this property will be very useful for some problems. If you do have any question, you can ask me. Okay, so complement part once again. So just try to concentrate on this part. Okay. So IA of x is basically 1 and 0 if x belongs to A and x belongs to, let's say, A complement. We can say if x doesn't belongs to A, that means x belongs to A complement. We can say like that. So 1 minus IA of x will be, so what will be the value of 1 minus IA of x? So 1 minus IA of x will be 1 minus 1. Okay. So 1 minus 1 if x belongs to A, okay, and 1 minus 0 if x doesn't belongs to A. So that's why it will be 1 if x doesn't belongs to A and 0 if x belongs to A, and which is similar to this quantity, or you can say like this 0 1. Okay, so this quantity or this form is exactly similar to this form. Now this is exactly I A complement and this is basically 1 minus I A of x. Is it okay, Kamesh? Okay, so let's go to the next part. So this is the third property, which is expectation of IA of X, and the fourth property, which is variance of IA of X. So what will be the variance? In the similar way, we can prove the variance part also, but I am just writing the result only, which is probability of A into 1 minus probability of A. Okay. Now this probability of A means basically, so we have written the form, probability of A means basically probability of capital X belongs to A. Okay. So that's why probability of capital X belongs to A into 1 minus probability of capital X belongs to A. And the fifth is basically the covariance part. Okay. So which is covariance between IA W. So W is another random variable, so IA W, or you can write as IA X also. So let's write IA X and IB, let's say X. Okay. So these are basically the covariance between two different indicator functions. Okay. Now this value will be probability of A intersection B minus probability of A into probability of B. Now the literal meaning, so literal meaning of this form is basically probability of X belongs to A intersection B minus probability of X belongs to A into probability of X belongs to B. Okay. So this is the exact form, but in short, we can write in this way. Now this is the concept, or this is the whole concept of the indicator function. So now let's go to the next part. An example. So use of this indicator function. So let x1 x to xn. So let x1 x to xn be IID random variables with CDF, let's say capital Fx. Okay, that means if they are IID, so that is basically they are independent and identically distributed. So independently and identically distributed means IID. So independent, obviously they are independent, and identical means each and everyone have the same distribution. So that's why each and everyone has the same PDF. Sorry, same PDF and same CDF also. So we don't know about the, let's say, the random variables are continuous or discrete. So that's why I'm denoting it by CDF. Now consider empirical CDF. Now what is empirical CDF? Now this empirical means, let's say, if any formula comes from the sample, or if any formula generated from the sample, that formula is called the empirical formula. We all know that there is a formula in descriptive statistic, which is the empirical formula in between the mean, median, and mode. Okay, so that means that formula comes directly from the sample, so that doesn't have any proof or anything. Okay, theoretical proof or anything. So consider the empirical CDF. So empirical CDF means if we generate a CDF, or if we create a CDF using the sample values, so that will be our empirical CDF. Now what is an empirical CDF? So which is denoted by fn hat x. And what does that mean? So you can, if we know the programming concept, if you all know the concept of programming, you can always understand this empirical concept. So let's say if we have capital Fx, so capital Fx, which is basically denoted by probability of capital X less than equal to small x. Okay, but in programming language, or you can say in sample, how can we get this value? As capital X is a random variable, so in sample or in programming language, we can create, let's say, n values. Okay, so we can get, if you have done, let's say, C or R programming, you can easily understand. So probability of capital X less than equal to small x can be denoted by, if we take n sample from the population, and based on this n sample, we just have to get the estimate, or we just have to get the empirical CDF. Empirical CDF means any CDF which is based on the sample values. So based on n values, we have to get those values. So that n values are basically x1, x2 and xn. Okay, now we have to get those number of, so this hashtag means number of. Okay, so number of those xi values which are less than equal to small x. So number of those xi values by total number of values, which is basically n, and this quantity will be the estimated value or the empirical value of the CDF. Okay, now what does this mean? This means, let's say if we have a random variable capital X and we have chosen n values from that, let's say 1, 5, -1, 2, 5, 6. Okay, so this is the value. Now if we want to count, let's say this is 3. So if we want to count the probability of capital X less than equal to 5, so if we want to count this, so how can we get that? So we can get using, we have to calculate using this sample only. Okay, so how can we get that? We just have to check the number of xi values less than equal to 5 by total number of values. Okay, now the total number of values is basically 1, 2, 3, 4, 5, 6. So that's why this n will be exactly 6. Now number of xi which is less than equal to 5, that means number of xi which is less than equal to 5 is basically 1, 2, 3, 4, 5. So these quantities are less than equal to 5. So there are 5 values less than equal to 5 and by total number of values. Okay, now if we want to calculate this probability under the programming section, or let's say under empirical section, then we can get in this way. So that's the approximate value of this probability. Okay, in programming language we all know that we cannot do the integration, we cannot do the differentiation in similar way like in mathematical sense. So we can do in this way, or we can get the probability in this way. And this is called the empirical CDF. That means a CDF which is based on the sample only. So the empirical CDF is defined as number of capital Xi less than equal to small x by n. Okay, now we can define this as 1 by n, so 1 by n, then within bracket summation of the indicator function which is -infinity to x, and let's just denote it by capital Xi and I running from 1 to n. Now what does this mean? So we have defined an indicator variable. So this is basically my indicator variable. So we have defined an indicator variable. Now this I -infinity comma x xi denote takes the values 1 and 0. So it will take the value 1 if this capital Xi belongs to -infinity to x, and 0 if it doesn't belongs to -infinity to x. That means we can say it will take the value 1 if xi less than equal to x, and 0 if xi greater than x. So simple. So we are checking about, or we are checking on each and every xi. So this xi, so this I running from 1 to n. Okay, so if we say, let's say I equal to 1, if we check on x1, so if x1 is less than equal to x, we take the value 1 and we are adding all of them. So for example, so let's try an example for that. Let's say capital X takes the values x1, x2, x3, x4, and the values are, let's say, 0, -1, 2, 1. Okay, and we are checking, we have to calculate this probability of capital X less than equal to 1. So how can we do that? So we have defined an indicator function, and the indicator function is applicable to each and every xi, and if first x1 is less than equal to 1, so if first x1 is less than equal to 1, then that I indicator function will have the value 1. So as this is less than equal to 1, now this is less than equal to 1, so that's why indicator function will take the value 1. This is not less than equal to 1, so that's why for this it is 0, and this is not less than, so this is obviously less than equal to 1, so that's why for this it is also 0. And then we take the sum, so we take the sum of all of these values, and these values of this sum is basically 3. So that's why we can get the total number of values which is less than equal to 1 is exactly 3. So that's why from this sum we can get the total number of values which is less than equal to small x. Okay, so from this example you can easily understand. So that's why f n hat x can be written in this way. Any question? So minus infinity x, basically xi is less than equal to x. So that's why xi less than equal to x can be written as xi is in between minus infinity to x. Okay. Now, this I of minus infinity to x, xi, so this is basically a random variable, and why? As this quantity depends on capital Xy, so this is basically a random variable. Now, this value or this random variable follows Bernoulli P. Okay, and why it is, or why it follows Bernoulli P? As we can see that I of minus x, so this indicator function, so this indicator function takes only 0 and 1 values. Okay, so that's why we know that any random variable which takes the value 0 and 1, so it will follow Bernoulli. Okay, now sum of any Bernoulli random variable follows binomial. Okay, so that's why sum of this indicator will follow binomial distribution. So where this small p, so this small p is basically, we all know that small p is the expectation of the random variable. Okay, now if we take expectation on indicator, we have defined the expectation part. So if we take expectation on the indicator variable, it will be the probability that so probability of this quantity. Okay, so just try to write, this is closed interval. Okay, as we have taken the value x, so that's why it will be a closed interval. Okay, now this quantity is nothing but capital Fx. As we have defined x1, x2, xn, each and every one has the CD of capital Fx. So this P is exactly capital Fx. So that's why Bernoulli P means Bernoulli capital Fx. Now, if we take the sum of all these Bernoulli random variables, yes, so if we take the sum of all these Bernoulli random variables, we'll get the binomial random variable. Okay, so that's why if we take the sum of all these Bernoulli random variables, so that will follow binomial. Okay, as we have summed over, let's say, n values, so it will be binomial n comma p. Okay, or you can write p equal to fx, so binomial n comma fx. Now This implies if we take expectation, so if we take expectation of this, so if we take expectation of this, so it will be n into fx. So simple. As you know, binomial, for the binomial random variable, the expectation is n into p, so that's why it will be n into fx. And this is 1 by n summation over I running from 1 to n minus infinity to x capital Xi equal to fx. Okay, so that's why we can easily see that this quantity, so this quantity which we have defined as fn hat x, so this fn hat x is an unbiased estimator of fx. Okay, so expectation of fn hat x is basically fx, or you can say like this is small x. The variable is capital X, but this is small x. So expectation of fn hat x is basically capital X, and this is true for all p. Okay, so this p for all p. So hence fn hat x is an unbiased estimator of fx. Okay, so this is a popular problem. So this is a popular problem from ISI. I have just forgot the year, but this is a popular problem from ISI, Indian Statistical Institute MStat exam. Okay, so why we take p equal to expectation of as in boundary, we indicate the probability of success. Yes, obviously. So in Bernoulli, P is obviously the probability of success, but P is also the expectation of the random variable. Let's say if capital X follows Bernoulli P, then expectation of X will be P. So that's why we have used this form. Okay. Okay, Akash. Okay, and the another part of the question is basically we have to find the MAC of this fn hat x. As fn hat x is an estimator of fx, so we have to find the MAC of fn hat x. Okay. Now, MAC of fn hat x is basically variance of fn hat x plus bias of fn hat x. Okay, but from, let's say, let these denote by star. So from star, as the bias of fn hat x is 0, as fn hat x is unbiased estimator, so that's why bias of fn hat is 0. So this is exactly equal to 0. So MAC of fn at x will be exactly equal to variance of fn at x, and we have defined the variance of integer functions as fn at x can be defined in this way, like variance of 1 by n summation of I minus infinity to x capital Xi. Okay, as you all know that these capital Xi's are IID, that means they are independent. So that's why we can insert this variance under the summation sign. Okay, so 1 by n square and then summation of variance of this quantity. Okay, now we have defined today that variance of any indicator function is nothing but probability of, so this is basically our set, let's say capital A, so probability of A into 1 minus probability of capital A. Okay, so that's why So it would be 1 by n square into, now this quantity is basically, if all the xi's are IID, so that's why this sum will be n into variance of I xi. Okay, or let's say you can write as x1, as all are IID. So if you write xi or x1, that doesn't matter. So it will be 1 by n into variance of any indicator function is probability of x1 belongs to this. Okay, or you can say like x1 into 1 minus probability of. Now what does that mean? So this quantity or this probability is exactly capital Fx. Okay, so this probability is exactly capital Fx, and this probability is basically 1 minus capital Fx. So MAC of Fn hat x is basically 1 by n into Fx into 1 minus Fx. Or you can say like variance, so this is exactly equal to variance of Fn hat x also. So MAC and variance are equal, and both are equal to this quantity. Any question? So the next concept is estimable parametric function. Okay, so what is estimable parametric function? Let's say, first of all, what is parametric function? So any function of parameter is called the parametric function. So let's say theta be a parameter, and then any function of that theta will be parametric function. So a parametric function which is, let's say, denoted by psi of theta is said to be estimable if expectation of t, so if, let's say, right, if there exists, okay, so this notation is basically there exist. So if there exists an estimator capital T of theta such that expectation of t equal to psi theta. Okay, so there are popular problems, let's say, to check that psi theta is estimable or not. So I'll do some examples. So a parametric function psi theta is estimable if we get a capital T such that expectation of t is equal to psi theta. So if this occurs, and if this is true for all theta belongs to omega, that means for all the values of the parameter space. So if this is true, we can say that this is estimable. So let's have some example for that. So first example, so if capital X follows normal mu comma sigma square, then the question is e to the power mu plus half sigma square estimable? So as we know that in normal mu comma sigma square, we have two parameters. One is mu and another one is basically sigma square. And this is a function of mu and sigma square, so that's why it is a parametric function. Okay, now the question is, this parametric function is estimable or not? Now you all know that the MGF, or you can define like mxt, which is expectation of e to the power tx, is basically e to the power t mu plus half t square sigma square. Okay, and this is the MGF of this capital X. Now if we set, let's say t equal to 1, so set t equal to 1, then expectation of e to the power t, if t equal to 1, then expectation of e to the power x will be e to the power mu plus half sigma square. And why? As t equal to 1. Okay, so in question, e to the power mu plus half sigma square is estimable, as we get a estimator which is capital T and which is basically e to the power x. So expectation of e to the power x is equal to that psi theta. Okay, or you can say like equal to that parametric function. Okay, so e to the power x is an unbiased estimator of this function. So clearly e to the power mu plus sigma square by 2 is estimable, and e to the power x is unbiased estimator of this. So e to the power x is basically the unbiased estimator of this quantity. So let's have another examples. So there is a result. So let's have an example first, then we write the result. So example, so let capital X1, X2, Xn follows let's say Bernoulli P. Okay, so X1, X2, Xn follows Bernoulli P, or you can say like X1, X2, Xn follows binomial P also, but okay. So X1, X2, Xn follows Bernoulli P. Can we estimate? So let's start with a first simple example. So let's start with the first simple example. Let capital X be a single sample. So to understand easily the concept, so let capital X be a single sample, not n samples or anything. So single sample from Bernoulli P. Okay. Now the question is, can we estimate, can P square estimable? Okay. Or you can say like, can we estimate P square based on capital X? So can we estimate P square based on capital X? So the solution is, now P square is estimable if, so let capital T of X as based on X, so that's why capital T of X is unbiased estimator of P square. So let's choose this. Okay, now if P square is estimable, then expectation of capital T, so if P square is estimable, then expectation of capital T will be P square. So then expectation of capital Tx will be exactly P square. Okay, now this can be written as like summation of T of X, sorry, T of small x, and for Bernoulli X takes the value 0 and 1. So that's why Px into probability of x equal to x equal to t square. Now if we write this like t0, so if we place the value 0 into probability of x equal to 0 plus x equal to 1 into probability of, let's say, t1 into product of x equal to 1 is exactly equal to p square. Now you all know that in Bernoulli, product of x equal to 0 is 1 minus p, and product of x equal to 1 is basically p. So that implies this will be like 1 minus p plus t of 1 into p is equal to p square. Now if we simplify all the parts, we can get p square plus, so just taking all the quantities on that side, so p square plus t0 minus t1 into p minus t0, and this is equal to 0. Okay. Now this is basically a polynomial in p, so that's why we can equate the coefficients on both sides. So if we equate the coefficient, you can get the coefficient of p square is basically 1, but on the other side the coefficient of p square is basically 0, as all the quantities are 0. So equating the coefficients, we get 1 equal to 0, and then t0 minus t1 equal to 0, and minus of t0 equal to 0. Okay. Now these last two equation, which is basically t0 equal to t1 and t0 equal to 0, so we can, let's say, we can say like these last two equations are valid equations, but this first equation is inconsistent. Okay. And why? One cannot be equal to 0, so that's why the first equation is inconsistent. Okay. And even the second equations are also inconsistent, as if t0 and t1 both are equal to 0, then tx always takes the value 0, so that means p will be 0, but p is not 0. Okay. P is the success probability, so that's why, but we can tell, if we tell that p is equal to 0, which is not exactly equal to 0, so this is always inconsistent, 1 which is equal to 0. So we cannot get, so hence we cannot get an unbiased estimator of p square. So we cannot get an unbiased estimator of p square based on capital X. Okay. So let's have a result for that now. So now another example, and from that from this example we can construct a result. So another example, let capital X1, X2, Xn be a random sample from, so let's say from Bernoulli P. Okay. So from Bernoulli P. Okay. Can we estimate p square unbiasedly based on x1, x2, xn? So the question is this. So can we estimate the p square? Now how can we estimate the p square? So solution. Now we have to estimate the value of p square using these x1, x2, xn, using these n samples. Now you all know that if x1 x2 xn follows boundary p and they are random samples, that means they are independent, then summation of xi, I running from 1 to n, will follow binomial n comma p. Now always try to remind that if x1 x2 xn follows boundary p, it doesn't always imply that summation of xi will follows binomial. Can you tell me, Anurag, which part? So hello Anurag, can you tell me which part? The second one means I think this part, t naught minus t1. Okay. So this if let's say from this part t naught is equal to t1 and from the last one t0 equal to 0. So if t0 equal to 0 and t0 equal to t1, that means both are equal to 0. Now if both are equal to 0, then capital Tx will only take the value 0. Now if Tx is 0, then expectation of Tx will be exactly 0. Okay, but we have chosen that expectation of Tx is basically equal to p square. But p is, we estimate that p is not equal to 0. If p is equal to 0, that means success probability is 0. But we cannot say like success probability is always 0. So that's why if we choose p not equal to 0, then tx equal to 0 is not acceptable. Okay, so that's why this can also be said as inconsistent if p is not equal to 0. But if we just assume p is equal to 0, then the first part will be inconsistent. Okay. Okay. Okay, so what I'm telling about that, if x1 x2 xn, always try to remind that fact, if x1 x2 xn follows Bernoulli p, it doesn't always imply that summation of xi will follow binomial p. Okay, so there must be a condition like if x1 x2 xn be random sample, or if x1 x2 xn be independent random sample. Okay, or let's say x1 x2 xn be independent, random sample is always independent. So if x1 x2 xn are independent and boundary, then only summation of xi will follow binomial. But if they are not independent, if they are dependent, then it will not follow, or the summation of xi will not follow binomial distribution. So try to remind that. Now, if capital T follows binomial n comma p, we all know that this result, so which is capital TPR, is NPR into p to the power r. If you don't know this result, try to find from the, let's say, basic distributional structure. So this TPR is nothing but the factorial moment. Okay, so factorial moment means, so let's say TP2 is t into t minus 1. Similarly, TP3, if we have TP3, that would be t into t minus 1 into t minus 2, and so on. We all know that for binomial, as it is discrete distribution, we always calculate the factorial moment. Okay, so this expectation of TPR is NPR into p to the power r. So that's why expectation of TPR by NPR, so NPR is a constant quantity, is exactly p to the power r, and this is true for any r. We can say like for any r greater than 1. Okay, or you can say like for any r 1 to n. Okay, so that's why we have to estimate p square. So unbiasedly, so unbiased estimate of p square will be and try to remind this result. This result is very much helpful. Okay, so try to remind this result. So that implies expectation of TP2 by NP2 is exactly equal to P square. So if we choose R equal to 2, so it will be exactly equal to P square. So the unbiased estimate of P square is basically this quantity, and this is a function of summation of xi. That means this is a function of these random samples. So P square is unbiasedly estimable based on x1, x2, xn, and TP2 by NP2 is the unbiased estimator of P square. Okay. Now here comes a result, and which is very important result for this context. So here comes the result, which is if capital X follows binomial n comma p. So that means, let's say like capital T, or we can get like summation of xi follow binomial n comma p, or let's say capital X individually follows binomial n comma p, then only and this is a very important result, so then only polynomials in P of degree less than equal to n are estimable based on capital X. Okay, now what is the implication of this result? So the implication of the result is basically, so it says we can estimate an p to the power n an minus 1 p to the power n minus 1 plus a, let's say a1x, sorry, a1p plus a naught. Okay, with an not equal to 0. So we can estimate any of this form. So that is, for example, we can estimate, let's say 3p square plus 2p plus 1. We can estimate 3p cube plus p. We can estimate like 5p to the power 2021 plus 1. Okay, so in this way, so any type of form. Okay, but always try to remind that degree must be less than n. Okay, so let's say if capital X follows binomial 2021 comma p, then 5 to the power, or let's say 5 into plus p. So this quantity is estimable, but 5 into p to the power 2022 plus 1. So this is not estimable. Okay. So if x follows binomial 2021 comma p, so this is estimable, but this quantity is not estimable, as you can see that this power is greater than 2021. So always try to remind this fact. And this is an important result, and you can get or you can take any type of polynomial. Okay. Now here, let's say a homework for you. So let's take a homework. So for the same problem, let's say capital X. So say capital X follows binomial n comma p, then is sine of p and cos of p estimable. So can we say that? So this is basically homework. Okay, so this is it for today, and this is our first class and first introduction class, and I will send the other class schedules and everything in the group, and those who join finally will, let's say, continue the other classes, and those who join finally will get the notes and everything and the problem sets and everything. Okay, so thanks to all. So I'm signing off now. If you do have any question, you can ask me on Discord, on WhatsApp, anywhere. So, so Pushpa, I will not follow any particular book. Okay, so I will follow different types of books, but I will recommend some of the books. Okay, so that you can understand. So I'm signing off now, and this video will not be private as this is our first introduction class, but the other videos will be always private, and only the registered candidates can see the videos. Okay. So yes, Kamesh. So I will send the name of the books. Okay. Okay, fine. So I'm signing off now. Okay, so thanks to all, and this video will not be private, so share with your friends to join as soon as possible so that we can start from the next class. And obviously, Shiny, so I have no plan to teach the other parts now. So this is the only lecture series I am now. So Anurag, I will tell you the class timings. I will just send you the detailed schedule of the other classes. Okay. Any more questions? Okay, fine. Okay, so I'm signing off now.